SwayamPrabha. Digital India. Educated India.
Welcome to the second lecture of the course Introduction to Robotics. So today we'll be looking at the various subsystems that make up a robotic system. We'll talk about the joints, then we'll talk about the links, and we'll talk about a degree of freedom. Now, different robots, depending on what are the joints that are used to make them, have different work volumes. So the shape of the work volume would depend on the joint structure now. So today's class will look at a degree of freedom and how do we draw the work volume of a robotic system. So we start off today's class looking at robot joints and work volume. And in the last class, we looked at a robotic system and the various subsystems that are involved in the complete robotic system. So these are links, and the links are connected by joints. So these are joints, and the joints can be of different types. Now this is called the end effector, or it can also be called a gripper, as in this case, and there could also be a tool. Okay, so end effector essentially includes the gripper or the tool. Now the links are connected by joints, and the base of the robot is fixed. So this is called the base, and it is fixed base. It does not move around. So in this course, we'll be looking at serial manipulators, and the base of the system will be fixed, and it is not going to be moving around. And the robot is controlled by a controller. So this is my controller, and the controller can be a PC, it can be a microcontroller, it can be a microprocessor, okay, or any other kind of controller. Now these are the various subsystems that make up a robot, and as we go along this course, we'll be looking at each of this. We'll start off today by looking at joints, then we'll look at kinematics. When you connect the joints, how do you perform the kinematics? That is, how do you go from one link to the other link? And then what is the shape of the work volume? And then finally we'll look at control systems. So let's start off by looking at different kind of joints. So the first kind of joint that has 1 degree of freedom is called the prismatic joint. Now, as the construction of the joint shows, there is a rectangular part. So this is a rectangular part which is mounted on another rectangular part. So this is a rectangular part, and this is the rectangular part which is mounted on there. Now, because the shape is a rectangle or a square, it cannot rotate about this axis, which means that if I give it a force here, okay, this cannot rotate about the axis, okay, as it is very clear. Why? Because it's a rectangle. But if I give it a force in this direction, or this direction, or this direction, it can go up and down. Okay, so this is what we call a prismatic joint. Now, what is an axis? The axis is the direction in which it can move. So this is my axis, this is the straight line. So this joint can move along this straight line. So the axis can go in the upward direction, or it can go in the bottom direction also, okay, because it can be up or down. So it's essentially a straight line which is extending in both directions. Now, what is the variable? The variable is a variable distance, which we call x. Okay. So we say that this prismatic joint has 1 degree of freedom. That means it can translate only in one direction, and it has one independent variable, which is x. And this is basically called a prismatic joint. So it cannot rotate about this axis, but it can only translate. So let me rub this off. It cannot rotate, but can only translate. What is the translational variable? It is x in this direction. So as is very clear from this figure, this block can move up and down, and it can go in a straight line, but it cannot rotate. And this joint, called a prismatic joint, has 1 degree of freedom. In short, it can be written as P. So when we say P joint, it basically means prismatic joint. It is also sometimes called translational joint. Okay, it can also be called translational joint, prismatic joint. They mean the same thing. It has a translational variable, and the variable is x, and it is 1 degree of freedom. Now, the second kind of joint is called a revolute joint, and the revolute joint is the one which is shown on the left side. And here we have a rectangular part. So, this is a cylindrical part which is mounted on a cylindrical part or a cylindrical pipe, and here there is a stopper. Okay, so the stopper is there. What is the function of the stopper? The stopper is to prevent this cylindrical part from coming down. So there is a stopper there. Now, what is the axis? The axis is again in this direction only, in that direction and in this direction. Okay, it's a straight line extending in both directions. Now, because this is a cylindrical part mounted on another cylindrical part, if we give it a force in this direction, okay, if I give it a push in that direction, what will happen is it will rotate about this joint, right? So it can rotate like that. And it can rotate means the joint variable is a theta. So the revolute joint has 1 degree of freedom. It has a rotating degree of freedom, which is theta. So theta is my variable here, and the degree of freedom is 1. Now, if I force it in this direction, if I give a force, what will happen is there is a stopper here and there is a stopper there. So this cannot go up and down. So there is no translation. Translation is not allowed, okay, on this joint. Okay, why? Because there are stoppers there. There is a stopper here and there is a stopper here. So this is a revolute joint. It has a rotating degree of freedom about the axis, and it has 1 degree of freedom. Now 95% robots will be made up of revolute joints. Now if you look at the joint on the right side, this is also a cylinder. Okay, so this is a cylindrical part which is mounted on another cylindrical part. So but the difference being that there is no stopper there. So there was a stopper in the revolute joint case, so the stopper is removed. Okay, so there is no stopper there. So now you can see from the figure that this revolute part, this cylindrical part, can rotate about the axis. Now what is the axis? Again, is the same axis. It is going in that direction and can go in this direction. Okay, so it's a straight line which is going like this. Okay, so this is my axis. So it can rotate about this axis. So if I give it a force from here, what would happen is it is going to rotate like this about the axis. So it has a what is the variable? The variable is theta here. Now, because there is no stopper to stop the translational motion, if I give it a push from here, if I give it a push from there, it can also translate. Okay, so it has two variables. One is theta and the other fellow is x. Okay, and it basically has 2 degrees of freedom. So this is called a cylindrical joint. It has 2 degrees of freedom. The previous one was a revolute joint. It has 1 degree of freedom. Okay, so what we see is that the revolute joint has 1 degree of freedom. It has only one variable, which is theta, and the cylindrical joint has 2 degrees of freedom. It has two variables. One is theta, the other one is x. Okay, so the previous joint what we saw was a prismatic joint. Then we saw the next joint is a revolute joint. Then we have a cylindrical joint. Now we can have another joint, another type of joint, which is called the spherical joint. This is also sometimes called ball and socket joint. It's also called ball and socket joint sometimes. Now, if you look at the construction of this joint, there is a ball here, which you can see is a spherical part. So it's a ball which is put inside another sphere. So this is my ball, okay, and it is put inside a cup kind of a structure. So this is another sphere where it is put inside. So that is the reason why it is called a ball and socket joint. So this is my ball and that's my socket. Okay, and the ball is inserted into the socket. Now, because it's a ball, it can rotate in any direction, and the socket is also spherical. So if we define 3 axes, one axis here, this is my x-axis, this is my y-axis, and that's my z-axis. Okay. Now this we have indicated 3 axes which are orthogonal to each other and named them as x, y, z. Now this ball and socket joint, because this is a ball, if you consider this to be the link, let me give this as a link. It can rotate about the x-axis. Okay, and rotation means it can is both clockwise and anti-clockwise. It can rotate about the y-axis. So my y-axis is here. Sorry, that's my y-axis. Okay, so this is my y-axis. It can rotate about the y-axis, and it can also rotate about the z-axis. Okay. So this ball and socket joint, the ball can rotate about x-axis, y-axis, and z-axis. What are the variables? Variables can be alpha, beta, and gamma, or we can call this theta 1, theta 2, and theta 3. Okay, so we have 3 axes, and each of this is the rotation about the respective x, y, and z axis. So a spherical joint has 3 degrees of freedom, which has 3 revolute joint, theta 1, theta 2, and theta 3. So it has 3 degrees of freedom. Okay, so the spherical joint, sometimes also called ball and socket joint, has 3 degrees of freedom. So it basically has the maximum variables associated with this joint. Okay, so now comes the question that if you want to make a robot, okay, which joint are you going to use? Now this is an interesting question. If we start off just looking from here, this is a prismatic joint. So if you're looking for motion in a straight line, okay, then you will need to have a prismatic joint. Then you may need a prismatic joint. For example, if I'm assembling something like this in straight direction, then I may need a prismatic joint. Okay, so this is one. Now if you are having a revolute kind of motion, okay, if you're having a rotating motion, then you could have a revolute joint, right? And if you're having rotating type of motion about 3 axis, then you could have a spherical joint. So in terms of the degrees of freedom, the spherical joint has the maximum degrees of freedom. So we might be inclined to think that it is a good idea to make robots with spherical joints. Now if you look at biological systems like our hands, our shoulder joint, you look at the hip joint, the knee joint, these are spherical joints. So here we have 3 degrees of freedom, about 3 axis, and that is the reason why we can move our hand like this. Okay, about 3 axis we can rotate, and it has 3 degrees of freedom at the shoulder. The reason being it has a revolute joint. Similarly at the hip also. The hip also has a ball and socket kind of joint, and that is the reason why we have 3 variables there, or 3 degrees of freedom. So it might appear that it's a good idea to make robots using spherical joints. Okay, but then if you look at industrial robots, they are made, 95% of them are made using revolute joints only. Now why is that so? Now if you think a little bit, if you look at the robot structure, okay, so we have a link connected by a joint, we have another link connected by a joint, and just like this. And how is the joint moved? So we have a motor. Okay, so we have a motor at the back, we have an encoder, position sensor, and we have a gear in front, and we give voltage to the motor rotates, and the link moves. That's how the robot moves. Now if you have a spherical joint, let me draw the spherical joint here. So this is my spherical joint, and so this is my x-axis, y-axis, and z-axis. Now if I try and move this, so what we are seeing is that the rotation motion about this joint, a revolute joint, in this particular case it is a revolute joint, is actuated by the motor. Okay, now in this case if I put a motor here, okay, I put a motor here, I put a motor here, okay, and I put a motor there. So what will happen is that the shafts of the motor are intersecting here. So what is going to happen is if I try and make a joint and try and actuate it using motors, they all intersect at that point. So if I try and rotate this like this, what will happen? It will start interfering with this one and will start interfering with that one now. Okay, so this is interesting to note that although the spherical joint has the highest degrees of freedom, okay, but controlling it by putting 3 motors like this is not possible. Okay, because all the shafts are intersecting now. Now you may be inclined to ask that in a biological system, how does it work? Now that's an interesting question, that in a biological system, in our arms, in the shoulder joint, if you look at our shoulder, how does the biological system work? So in the biological system, if you see, basically our hands are, okay, if this is my hand, okay, these are actuated by muscles. Okay, so this is a muscle which is actuating the motion of the hand. So if this muscle contracts, this will relax, and if this one contracts, then this will relax. So essentially biological systems have linear actuators, okay, not rotating actuators like joints and like motors. So in a biological system, if this muscle is contracting, so if you look at our hand, if this muscle is contracting, then what will happen? This muscle will relax. So it is doing that in pairs. So although the muscles could be interacting with one another, they can relax and contract, and they are linear actuators, and because of which in the human body we can very easily move the shoulder, and there is no problem of these 3 joints or these 3 axes which are intersecting at a point. This is something very interesting. It's something to note that biology prefers this ball and socket joint, but case of robots we normally prefer revolute joints. Okay, essentially there is a control problem. In short, we call this a P joint, prismatic joint, and this one is called a revolute joint, so we call it R. Okay, this one is called a cylindrical joint, so we call it separately. It has R and a P. Okay, revolute and prismatic, it has both. And this one is called a spherical joint. It has 3 R's, 3 rotation axes. Okay. It stands for 3 degrees of freedom. Now we have also seen that controlling a biological joint or a ball and socket joint is difficult because the three axes are intersecting. Okay, whereas in biology, because we are using linear actuators, our muscles are linear actuators, this problem doesn't come up. Now we come to the important question that how many degrees of freedom must a robot have? Now it depends on the task. Okay, so by connecting different joints, we can make a robot, and the total number of these joints will make up the total degrees of freedom of the robot. So if it has five revolute joints, that will be 5R or 5 degrees of freedom. So how many degrees of freedom must a robot have depends on the task. Now what is the task you're going to do? That is one. The second is the task should be inside the work volume of the robot. Okay, because as I'll explain that the end effector can move inside the work volume only. So you cannot have a task which is outside the work volume. Now, what do you mean by how many degrees of freedom a robot must have depends on the task? Let's look at this very simple task. So here we have an object. So let's say I have my mouse, and I pick up this object, this mouse from here, and I keep it here. Okay. So what is the task? The task is very simple. This is a computer mouse, as you can see. So this computer mouse I'm going to keep on the table. I need to pick up this mouse from here. A robot will pick up the mouse from here like this and take it like this and keep it here. Similarly, you can imagine on your table that there is a pen which is there, or there is another object like a mouse. You're picking up the object and keeping it somewhere else. So let me draw it very quickly. So this is my table, okay, and I have kept a rectangle. Let me say this is a rectangular mouse, okay, or rectangular box. I want to pick it up from here and keep it there. I think the problem is clear. We have kept a box on a table. I want to pick up this box and then put it somewhere else. How many degrees of freedom are required for this task? Okay, so now if you just think, you are inclined to say 2 degrees of freedom are enough. But please think about this carefully. How many degrees of freedom are required to pick up this object from the table and keep it somewhere on the table again? Okay, so how do we define the problem? So first we need to put our axis, because we need motion along an axis, either rotation or translation, but it is about an axis. So let us put our axis. This is my x-axis. I'll just change the color. So let me put the axis. This is my x-axis. This is my y-axis. Okay, and that's my z-axis. Okay, so 3 axes I'm putting there. Now when I'm saying that I need to go and catch this object, what does it mean? So let us say that the CG of the object is there. Now the object is lying on this table. Now this table is xy plane. So this can have 2 coordinates. It can have x and it can have y. Okay. So this object could be anywhere on this table. It could be here, it could be here. Okay, it could be somewhere else, it could be here. So what does that mean? That the CG of the object could be in different points on this table. Okay, and the CG is having 2 coordinates, x and y. It has a z also, but at the moment let's say that we are considering the object kept on this table. So as long as we control that x and y, then I can catch the object or place the object anywhere on this table. So there are how many independent parameters? There is x and there is y. So there is 2 there. Okay. So after catching the object, what I need to do is I need to take it up. Okay. So I need to take it up like that. Okay. And then I need to move like this. Then I need to keep it down there. Okay. So I need to take it up. Then I need to move like this, and then I need to keep it down. So to take it up means I need to move along the z-axis. So this is my z direction. So I had 1 degree of freedom, 2 degrees of freedom, x and y. Now I have 1 more z which is required. Then I want to move in this direction. Now moving in this direction means x and y only. Okay. So this is already covered. So this is moving in the xy plane. So it is xy. It is already covered. Going down again means z. Okay. Z is already covered. Okay. So now we see that we need x, y. So how many are required? X, y, and z. Okay, so that means 3 degrees of freedom. Now is 3 degrees of freedom enough? Please think about it. Now when we are saying you need to catch an object, what does this catching an object means? That I will need a gripper that will hold a gripper, a robotic 2-finger gripper or 3-finger gripper. You'll have to place 2 fingers on this side and 2 fingers on that side. Okay, or 2 fingers this side and 2 fingers that side. That's how you catch. That's the meaning of catch. Okay, so if I take the top view of this, so let me draw the table and the object again, because we need to understand this very carefully. This is my top view. Okay, this is my top view. I'm looking from here. So that's my top view. And on this object, we have, on this table, we have the part which is kept like this. Okay, it's a rectangular part and it is kept like this. Now I need to catch. So if you can imagine, the robot will catch it. How will the robot catch it? It has to place its fingers along this direction or along this direction. That is one way. The other way it has to catch it, it could place its fingers this side and this side. Okay, so it basically means that this object could have different orientations. What I mean is that the object could be placed like this, the object could be placed like this, or the object could be placed like this. In all cases, the fingers should be able to align along the sides to catch, otherwise it will not be able to catch. So it basically means if the finger has to align about this axis, about this vertical axis, okay, this axis which is coming out of the plane, then it needs to rotate about this axis. So that rotation has to be there. Okay, so I need to have a rotation also to catch. So there is a rotation axis which is theta there also. So how many degrees of freedom do I need? X, Y, Z and theta. So which is equal to 4 degrees of freedom. Okay, so to do a very simple task like this, like you have a mouse, you catch it and you pick it up and put it somewhere else, then it needs 4 degrees of freedom. By the rotation, I mean, if you look at the mouse here, I can place my finger like this. Okay, so I hold it like this, but if the mouse has been rotated, I have to rotate my finger also, otherwise I can't catch. Okay, so I need this theta about the axis. So which is the axis? The one that is projecting outward like this. So I have one rotation that is required at the wrist of the robot for aligning the object. So this means that the minimum that we need is 4 degrees of freedom, okay, for this simple task of picking up this object and placing it. Okay, I hope please do this yourself and see what is the correlation between the real world and this degrees of freedom. Okay, in robotics we need to correlate between the action in the real world and the mathematics of how many degrees of freedom in terms of equations or whatever. Okay, now an interesting point here is, does it depend on the shape of the object? I showed a mouse. So this is a mouse. It has it's a rectangle. Okay, what you're seeing is a rectangle. Now if it was a cylindrical part, this pen is cylindrical. Okay, so if I have to catch it, or let's take another example. I want to catch this bottle. Okay, so this is a bottle. Okay, and you want to catch it, it's a cylinder. Okay, so I can catch it anyway, and that action and that position of the fingers will not matter. Okay, so I hope you understand that now on the table, if I keep a cylindrical object on my table now, I have this, this and this, and I have kept a cylindrical object like this. I want to catch the cylindrical object, and so the cylindrical cylinder now, okay, and I want to keep it somewhere else. I want to keep it here. I want to position, pick it up from here and keep it here. Okay. Now how many degrees of freedom are required? Again, we use the same logic in saying that I had put my XYZ axis, X axis, Y axis and Z axis. Okay, so this could be placed anywhere on the table, so that's XY. It has to be picked up like this and put down like this, so that is a Z. It has to move like this, which is again XY. So I have XYZ. Now to catch the object, if I take the top view of this object, if you are looking at this table from the top, from here, this is my top view. Okay, then what we see is, I'll be seeing the table like this, okay, and the cylinder is placed on the table like this. Now to catch it, I have to place my fingers, but now, unlike the case in the rectangle, I can place here, or I can place here, or I can place here, I can place here, I can place there, I can place there. As long as it is diagonally opposite, it's fine. And because this is a circle in the top view, okay, it doesn't matter where you're placing your fingers. So you have the freedom. So this degree of freedom that we had, theta, is not required here. Okay, because you don't need to rotate when you're catching. It's a cylinder, you can catch it in any orientation. Okay, so in this particular case, it is X, Y, and Z. Okay, so I hope you understand that the task and the kind of object and the way you're going to place it all depends on how many degrees of freedom you want. Now let's go back to this problem again. Okay, the mouse or the rectangle which is being kept on the table. Now suppose I want to place the rectangle at a particular angle. Okay, what I mean here is, I have the table and I want to place the rectangle. In this particular case, this surface was flat, and it was being kept on the flat surface. Now suppose I want to keep this rectangle at an angle like this. Okay, suppose I want to do that. Okay, suppose there is a small triangle kind of, suppose there is a triangle kind of object on which I want to keep the rectangle now, if you can imagine. That means the bottom surface of the rectangle must make an angle there with the surface of the table. I want to keep the object like this now. Okay, that means I have added one more angle here. Okay, so x, y, z, theta, there is one more, there is alpha. Okay, now suppose I want to keep it with two angles to the surface. So this is a surface, that is another surface. So this is one angle. I can keep it. I can keep the rectangle like this also. Okay, so where it is standing on that edge only, on that corner point. So there is one alpha here, and there is another angle there. Let's call it beta. Okay, so it is making two angles with the surface of the table. So I have to add one more beta. So how much do you get? X, y, z, theta, alpha, beta. Okay, so there are three x, y, z's, three coordinates, and there is alpha, beta, and theta, which is another three. So three here and three here. Okay, so it is total of 6. Okay, so in general, a body in space, a rigid body in space, can have 6 degrees of freedom. We know that, right? 3 translations and 3 rotations. So that is where the 6 comes from. So if you're trying to keep the body on this table, then depending on the shape of the body and the angle with which you want to keep the body, at most they can be 6 parameters. Okay, if there are no other constraints. So that is where our 6 degree of freedom comes from. And in this particular case, we have seen that if you want to keep it flat, it is 3 degrees of freedom. If you want to keep it at an angle, one angle with the table surface, then it is 5. And if you want to keep it with two angles on the surface of the table, then it is 6. Okay, and the body itself, because this is a rectangle, it has 1 degree of, it has 1 rotation is required at the end effector. Okay, so this is how we get our 6 DOF. So it's very, very important that we understand that the shape of the object, how you are keeping it, what are the angles you are making, all of them contribute to the degree of freedom. Now, if you need more degrees of freedom, okay, then are there cases where you can need more degrees of freedom, more than 6? So we have seen that with 6 you can keep with any angle and you can catch an object of any shape. But if you are doing a task something like this, for example, we have a passage like this. Okay, this is a very narrow passage. Okay, and there is an object which is kept there. I want to go and pick this up. So if a robot is here, let's say there is a robotic system here, it has many links. The robot is going like this, like this, like this, and like this, trying to catch it. Okay, the moment it has entered this hollow section, what will happen is some of the degrees of freedom of this joint will be lost. Why? Because it can't move up and down, it's constrained now. So in that case, although this keeping a cylinder on the table is requiring less degrees of freedom, okay, less than 6 or at most 6 depending on the angles, okay, but now if you want to go and catch it, because there are constraints here now, okay, constraints which are limiting the motion of your joints, you may need more than 6 degrees of freedom. So greater than 6 DOF may be required, and these are systems which are called redundant manipulators. So I'm trying to explain that what is the degree of freedom, how do you decide the degrees of freedom, and when do you need more than 6 degrees of freedom. Okay, so as we go along, we'll be looking at this in more detail, but this is a very brief introduction of what is a degree of freedom, how do you decide how many degrees of freedom are required for a task, and then do you need more than 6 degrees of freedom. So normally we need 4 for catching a rectangle and keeping it on a surface. For a cylinder, 3 is enough. Okay, now if you add one angle of that object you're keeping on the table, then it becomes 5. If you add 2 angles, it becomes 6. Okay, and if there are constraints on the link motion, now they can become 7, 8 in that order. Okay, so in general, we say a general purpose robot has 6 degrees of freedom, and I hope you understand why it is 6 degrees of freedom. Now, by making different robots with different kind of joints, we can get different types of robots. So if you make a robot only with prismatic joints, then we get what is called a Cartesian robot. Now this Cartesian robot has 3 degrees of freedom. It is 3 DOF, and it has 3 prismatic joints. That is the way we name it. 3P meaning 3 prismatic joints, and it has 3 degrees of freedom. Now, what will be the shape of the work volume? What is the work volume? When these joints are moving, the end effector of the robot will carve out a region in space, okay, inside which it can position its end effector. So we need to find out what is the shape of this work volume. So this will be called the work volume or work area. Okay. Now, how do we draw it? So you can start off by looking at what are the 3 degrees of freedom. So this is the side view. So this is one joint which can move like this. This is one joint here. This is another joint which can move up and down in straight lines because they are prismatic joints. Now when we look at the top view, from the top we get is this one. So the whole base of the robot can move in this direction, okay, because there's a prismatic joint here. That's a prismatic joint also. So now when we draw the work volume, how do we start? So we first start off with, in the side view, let's start off with the first joint which is fully extended. So this is one joint which is fully extended, which means it can come from here to here. Okay, so when this joint is moving from here to here, it is creating a straight line. It is generating a straight line. Okay, because it's a prismatic joint. So one end is here, the other end is there for the joint motion, and we are getting a straight line here, corresponding to this degree of freedom. Next is D2. It is going to move from here to here, up and down like this, okay, in a straight line. So this straight line is getting swept down like this, if you can imagine. The straight line is coming down like this, and in each region it is coming like this, like this, like this, until this end. So it is ranging from here to here. What are we getting? What is the shape of the area? It's a square or a rectangle, depending on the lengths. If the lengths are equal, it's a square, otherwise it's a rectangle, right? So what we see is, how do we start drawing? We start from one end and go to the other end, and in this case we start from this end and go to that end. What we get here is a square or a rectangle. Now if I see from the top view, this is a plane. You can imagine that this is this square or rectangle is a plane. So when I see from the top, I'll be seeing this edge. So it's the edge view of a plane, which is a straight line. So this is my straight line which is coming on the top view. Now the base of the robot can also move like this, so which is meaning that this straight line is getting swept like this. So the straight line is coming like this. Okay, these are all continuous, okay, till this end. So what is the shape we are getting? We are getting a rectangle or a square again, depending on the lengths. Okay, so if I combine the top view and the side view, what is the shape I'll be getting? I'll be getting the shape of a cube or a cuboid. So it will be like this. Okay, so it's a cube or a cuboid. Okay, so that is the shape, a cube or a cuboid. And anywhere inside this, the end effector can go. So the end effector of the gripper can be positioned anywhere inside this cube or this cuboid. And the shape of the work volume is a cube or a cuboid for a Cartesian robot. Now, if you look at a cylindrical robot has one prismatic joint and 2 revolute joints. Okay, so it has cylindrical robot has 1 revolute and 2 prismatic. So it is 1 revolute and 2 prismatic joints, 2p. Okay, so these 2 prismatic joints are, one joint is this one, it can translate. This is the other one which can also translate. The revolute joint is, if you look from the top, this can rotate about this axis. The axis is coming out of the plane. Okay, so it is rotating. So that's my revolute axis. Okay, now let's start drawing it again. So this joint, which is marked D3, extreme ends are one end to the other end. So it can go from here to here, okay, which is a straight line. It can move. So this one is generating a straight line in this configuration. Okay, in this configuration, it is generating a straight line. Now, the second joint is moving, so the straight line is coming down. Okay, the ends is from here to here is the end. So the straight line is coming down, 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 down like that till here. So what is the shape we are getting? The shape we are getting is a square or a rectangle. Okay, and it's a plane. Okay, it's a square or rectangle depending on the dimensions of D3 and D2. If they are equal, it's a square, otherwise it's a rectangle. Now, when we are seeing from the top this planar figure, what we are seeing is the edge view will appear as a straight line. So this is my straight line now. Okay, so that is my straight line that we are getting. Now, this is a revolute degree of freedom. So it is theta, it can rotate from one end here to the other end there, like that. So this straight line is getting swept like this, and it is generating this shape. Okay, so this is my shape from one end here to the other end there. This is the limits of the joint. So what is the shape we are getting? We are getting this kind of a shape. Okay, we are getting one bigger circle outside and one smaller circle inside. Now, if I combine this and this, what will be the shape of the volume? So it is going to be a a hollow cylinder kind of thing. Let me draw it here. So it's like this. So that's a bigger cylinder, and inside there's a smaller cylinder. So okay, so this is my bigger cylinder and this is my hollow cylinder. This is my cylindrical shape. Okay, so this is the shape I'm getting. Okay, so it's a hollow cylinder, is the shape of a cylindrical robot, and I hope you understood the way it is drawn. Once you understand that, it's very easy actually to draw the work volume of different types of robots. Now let's look at a spherical robot. Now a spherical robot is something like this. It has a spherical joint. Okay, so I'm just drawing the spherical robot. Now let me draw it a little bit on the left. I have to draw the left side view and the right side view also. So this is my spherical robot, and it has, okay, so this is the base of the spherical robot, and okay, so this is the side view of the spherical robot. On the top view, the spherical robot can be something like this, and this is the front. Okay, this is the spherical robot from the top view. Now, what are the degrees of freedom of this? This is my end effector. Okay, now what are the various degrees of freedom? On the top view, it can rotate about this axis. If you can see, the perpendicular axis is here. Okay, so there is an axis like this. Okay, this is the top view. So from the top view, when I see this axis as a point, and it can rotate like this. So there is a theta there. Next is, it can rotate, the axis is coming out of the plane, if you can imagine this. So this can rotate about this axis. Okay, here there is a rotation joint. Okay, so it can rotate. So there's another theta 2 there. And this is a translating joint, which can go up and back and front like that. So that's theta 1, theta 2, and d3. Okay, so what is the shape of the work volume of this spherical robot? We start off by drawing. So d3 can go from here to there. It's a straight line. Okay, so this is my let's say this is my straight line. Okay, d3 is going to the extreme extended position, to the extreme retracted position. Then theta 2 is moving. So theta 2 maybe can go like this from here to here. So the straight line is being swept from here to here. Okay, so the theta 2 is about this axis, and it is rotating like this. So what we are getting, the straight line can rotate like this, and we are getting that sector. Okay, this is my straight. This is the shape of the shape of the area that it is going to carve out in space. So what is the shape? The shape is like this, like this, like this, and like this. Okay. Now when I'm seeing from the top view into this area, what I will be seeing is the straight line, because this is a planar surface. Okay, it is a sector of a there is a circle here and there is a circle here. But when I'm seeing this from top, what will happen is I'll be seeing a straight line like this. Okay, corresponding to the maximum and the minimum retracted condition of d3. Now when I'm using the theta 1 is rotating, so it is rotating from one end. Let's say it rotates from one end to the other end. So this is going to be rotating, and it will come till there. This will rotate and come till here. Similarly, this fellow will rotate and come till there, and this will rotate and come till there, if you can imagine. Okay, so this is rotating and coming till here. Okay, so this is my rotation. These are straight lines which are rotating. Okay, so what we are getting is this is the shape on the top view. So if I combine this and this, what will be the shape of the work volume? So the work volume is going to become spherical. So it will become spherical with some funny shapes in between. Okay, so it is going to become a part of a sphere. Okay, so the work volume is going to become spherical. So when I combine from the top view, if you can imagine this, the left side figure plus the right side figure, so it is going to become a sphere kind of shape. Okay, so so this shape is going to become spherical. Okay, spherical in shape. So in that spherical part, there will be some part inside which is not there, this part, but the other part is going to be a part of a sphere, if you can imagine how this will look. So this is a spherical robot which has two revolute joints and one prismatic joint. Okay, and this is what the shape of it looks like. Now, let's look further. We have looked at a Cartesian robot, then we have looked at a cylindrical robot, then we have looked at a spherical robot. Now let's look at robots made up of revolute joints. The simplest one is a 2R planar round. So this has two revolute joints, and let us see how do we draw the work volume of this. Most of the robots are articulated and they are of this shape, so this is very important to understand how do we draw it. So let's start off by saying that this is planar. Okay, so this is the fixed base, this is one link, and that is another link. Okay, so this is my theta 1, that's my theta 2, this is L1, and that is L2, link lengths. Okay. Now let us make the assumption that theta 1 and theta 2 can only move by 180 degrees. Let us make this assumption just to understand. Okay, so first of all, it is planar and it can move only on this plane, it cannot come out of the plane. There are two axes. What are the axes? One axis is here, another axis is there. It can rotate like this, okay, or it can rotate like this. So this can go anywhere on this plane, but it cannot come out of plane. Okay, these are the two revolute axes. One revolute axis there, one revolute axis there, and these are the axes. Now it can rotate 180 degrees. So let's start off by drawing by completely extended condition. Okay, so in this condition, let us say that it is at 0, 0, 0, and it is completely extended. Now first we move, what do we do first? Move theta 2 by 180 degrees. Okay, so theta 2 is going to move by 180 degrees, which means that it will come from the top position. It will have a semicircular arc and come here like this. Okay, so this is the first one I'm getting. Okay, it has come like that. So if you can imagine, this link has rotated about this axis and it has come down like this. So that is my first move, theta 2 by 180 degrees. Then move theta 2 or theta 1 by 180 degrees. So what will happen is now theta 1 is moving by 180 degrees. So there will be one more curve here like this. Okay. So what has happened? This has come this side now. Okay. Is it okay? So I hope you understand that how these two circles were formed. First we moved theta 2 by 180 degrees. Then I moved theta 1 by 180 degrees. It has come like this now. So on the inside I get two curves. Then what I do, so this is my first step. The second step is fully extended theta 1 plus theta 2. So fully extended for theta 1 and theta 2. Okay, I will move only theta 1 by 180 degrees. So I'll move theta 1 by 180 degrees. So what I'm saying is it is fully extended condition, the blue line, and I'm going to move, so it is fully extended, and I'm going to move only theta 1 by 180 degrees. So I get one circle like this. Okay, have you followed? So first what we did is we got the inner two circles, then I extended both the arms like this, and I rotated theta 1 by 180 degrees. So what we got is this outer curve, and this outer curve is going to become L1 plus L2. Okay, that will be the radius of the outer curve. Now when I open theta 2, what is going to happen is it will come like this, and that's the complete figure. Okay, I hope you can visualize this. You need to draw it once and then it will become clear. So we do this in two steps. The first step is that we move theta 2 in the fully extended condition. Okay, then we move it by 180 degrees, we get the inner curve. Okay, then we move theta 1 by 180 degrees, we get the second curve. Okay. And then for the outer curve, in the fully extended condition, we move theta 1 by 180 degrees, so we get the outer curve. So this is the shape of the surface that we are getting. Okay, now something important here is when there are 2 degrees of freedom, you get 2 inside curves. Okay, so there are 2 inside curves like this, but there is one outside curve like that. The outside curve is always L1 plus L2. The inside curve is going to become here. Okay, this is my inside curve 1, this is my inside curve 2, and there are 2 revolute joints. The outside curve is always one curve. Now, how did I get this one? So essentially, when I open theta 2 from back from 180, so this curve I'm getting back from 180 to 0 degrees, let's say. Okay, it will open like this, it will come till here, so it will become the ulta of this one, it will become reversed of this one, right? So that is my reverse condition. Okay, so what we are getting is this shape of two curves inside and one curve outside. Okay. And please draw it by yourself once so that you understand how it is drawn. Now let's move on to an articulated robot which has 4 degrees of freedom. So there are 4 DOF degrees of freedom. There are 4 revolute joints. What are the axes? And okay, I just forgot about mentioning the axis, but it was quite clear here that when we say an axis, what is the meaning of an axis? So the axis here is this one is one axis. Okay, so we have one axis here, we have one axis here, and we have one axis on this side. Okay, similarly on this one, what are the axes? Axis of rotation or translation. We have one axis here, we have one axis here, and we have one axis which is coming out of the plane like this. So this is a rotation like that. Okay. What is the axis here? This I had explained that there is one axis. This is one axis. Okay, this is one axis, which is this one. Then there is one axis here, and there is another axis which is coming out of the plane, which can rotate about this. It's three axes. Sorry. This one, what is the axis? The axes are perpendicular like this. Like this, they can rotate. Okay. Rotation means clockwise and anti-clockwise. In this case, I have put a constraint of 180 degrees just to understand the shape. Now, let's look at 4 degree of freedom system. What are the axes? So we have theta 1, which is like this. Okay, it can rotate about that. Now, when I see from the top, what I'll see, this is the point. So this is my point. So it can rotate like this. That's my axis, first axis. The second axis is this one. So the axis is out of the plane. Third axis is here. Fourth axis is there. So this can rotate like this. This can rotate like this. This can rotate like this. This axis are pointing out of the plane. So please note that they are perpendicular to the plane. So this is the 4 degree of freedom system. How do we draw? Now, in the previous case, I explained the 2 degree of freedom system. Okay. Now this is 3 degree of freedom. So essentially, it is exactly the same. So there is 1, 2, and 3. The previous one had 2. This one has 3. So how are you going to draw? I'm going to draw exactly in the same way. First, I will see the completely stretched position. Okay, this is fully stretched. Then I'll move this. I'll get one curve. Okay, I move this joint. Then I move this joint. I get one more curve. Then I move this joint. I get a bigger curve, like that. So I get 3 small curves. So if you see here, this is fully stretched condition. I move the small fellow. Okay, so first I move this one. Then I move this one. Then I move this one. So first one I move the first joint, which is this one. I get that curve. Then I move this joint, I get this curve. Then I move that joint, I get that curve. Okay. How many curves did we get? 3 curves. So there are 3 degrees of freedom. We got 3 curves. In the previous case, there were 2 degrees of freedom, and we got 2 curves. Okay. So here I have 3 degrees of freedom, and it is giving us 3 curves on the plane. Okay. Now, what about the outer shape? The outer shape is fully stretched, and I'm going to rotate only theta 2 by 180 degrees. So it goes fully like this, like this, like this, and it comes like this. What is this equal to? L1 plus L2 plus L3. That's the radius. So what does the shape look like? The shape looks like something like this. Not something like this, but it looks like this. Okay. So this is the shape from the side view of the work volume, making an assumption that your theta 2, theta 3, and theta 4 have joint limits of about 180 degrees, or they have joint limits. Okay, that means they cannot rotate 160 degrees. If they rotate 160 degrees, the shape will be different. Okay, so now let's look at the top view. So if I look at the top view of this shape, what will we see is a straight line. So there'll be a straight line like this. Okay, because this is a plane, and when you're looking at the plane from the top, what you're seeing is an edge view, and the edge view will be a straight line. Now, the theta 1 joint limit can rotate from here to here. This is the joint limits. So this straight line is being swept like this, like this, like this, like this. Okay. Okay. So this is and so what is the final shape we are getting? The final shape is like this. Okay, so the final shape is one end is there, another end is here. So there's one circle inside and another one outside. Okay, that is the final shape that we have got in the top view. This is my top view, right? So if I combine this one and this one, what will be the shape? So it will be part of a sphere. Okay, so it will be spherical, and inside there are going to be parts which are going to be left out. Okay, so from the top view, when I combine this one and this one, what will be the shape? It will be part of a sphere. Okay, so it is going to be spherical again. So it is going to become spherical. Spherical shape. Okay, so this is how we are getting the shape of the work volume of different kind of robots. Now, in assembly application, what we do get is we need the motion in straight lines. Okay, now robots are used for spot welding, spray painting, and in the electronics industry. Okay, in the electronics industry, we require assembly of electronic components, which are normally chips. So when you assemble chips, however, you know that computer chips, they look like this. They are small rectangular body and there are legs, okay, very thin and multiple legs. When we are assembling these chips, we have to move the chips and align them very accurately on the motherboard. So if I say this is my motherboard, there will be corresponding holes for the legs, and the legs have to be inserted into those holes very, very accurately. So if there is little bit of misalignment, what will happen? The chips will break. So in this kind of assembly, what we require is a straight line motion. Okay, and in order to provide the straight line motion, we have one prismatic joint. So this is a SCARA robot, which is essentially used for electronics assembly, and it has 4 degrees of freedom. It has 4 DOF, and it has 3 revolute and 1 prismatic joint. One prismatic joint is essentially for this assembly of electronic components for motion in a straight line. Now, as we'll go along, we'll also see that if you want a revolute joint robot to do straight line motion, it is actually very difficult. Okay, it can be done, but it's difficult, and that is why in electronic assembly, this SCARA robot, which is called selective compliance assembly robot arm. That's what the name SCARA comes from, selective compliance assembly robot arm, and it is basically used for electronic assembly. Now, what are the 4 axes? What are the 4 axes of this robot? The first axis is here. Okay, it's a rotation axis. Second axis is there. It is a rotation axis. The third axis is a translational axis. This one is going up and down, which is here. That means this part can move up and down. That is the translational axis. And the fourth axis is here at the wrist, which can rotate. It is essentially for catching the part in any orientation. So this is revolute, this is revolute, this is prismatic, it is revolute. These are the 4 axes of the robot. Now, how do we start drawing? Now, if you look from the top view, okay, this robot, there is a revolute axis here and there's a revolute axis here. So there are 2 planes. One plane is the side view, which you are seeing here, the side plane, and this is the top plane, the top view. So if you are drawing the work volume, how should we start? That is, you look at the prismatic axis, and what is the motion of the prismatic axis? It's a straight line here. It can go up and down from here. Now this up and down from here can be rotated about this axis and about this axis, if you can imagine. Okay, so if you're seeing the top view here, what we are getting is the big cylinder, which is the sum of this length plus that length. So we get one outer cylinder, an outer circle. And when I'm folding this about this axis, I'm folding this about this axis, I'm getting, when I'm folding this fellow like this, it is coming till here. Okay, so what we are getting is a smaller cylinder. Okay, so this is my outer cylinder, outer circle. And when I'm rotating this axis like this, it is coming till this point. Okay, so I'm getting another point here. Now, when the joint number 1 is rotating, what is happening? This point is being rotated like this to get a smaller circle. So this is one smaller circle, which is because of rotation of theta 1. The outer circle is because of L1 plus L2. So when it is in fully stretched condition, you'll get this circle. When this fellow is rotated and it is closed rather, then we'll be getting this inner circle. Okay, so what we are getting is the straight line here, which is being swept from the top view like this. We are getting two circles. So when you're seeing this from the side view, it's a cylinder, right? So a cylinder from the side view looks like a rectangle. Okay, so the shape of the work volume, if I draw it in 3D, will be something like this. So the 3D shape of this is going to become one big cylinder, okay, and a smaller cylinder like this. Okay, so this is the shape of the work volume. Okay, and when I'm looking at it from the side view, a cylinder will appear to be a rectangle, right? So when I'm seeing from the side view, I'll be seeing this only, and that is what I'm seeing here. Okay, that is my side view. So how are we drawing the work volume? We see the fully stretched condition of the prismatic joint. It becomes a straight line here. Then I look at the top view, and I have two circles. One is the sum of this length plus that length. Okay, that will give me the outer circle. Then when this length is folded, so when this fellow is rotated, what will happen? This will be coming back and there will be one small point there. Okay, then I rotate this one again, so I get a small circle here. Okay. And then when I combine the side view and the top view, what I get is a cylindrical part or hollow cylinder. Now we need to answer this question of optimal link lengths. We have seen what will be the different shape of the work volumes, and depending on what kind of structure you want, towards the end we'll go and talk about the load carrying capacity, the structural index, which robot has the maximum load carrying, which has the maximum volume to the degree of freedom, okay, ratio. Those things we'll be covering a little bit later. But this basically shows us that there are different work volume shapes, and depending on what kind of shape you want, you have to have that corresponding type of joints. Now it brings us to another important question: what should be the optimal link lengths? So we look at this 2 degree of freedom robot, and we want to know what should be the ratio of L1 and L2. So what should be L1 by L2? It should be how much? Okay, suppose it is A, what should A be equal to? Now how do we answer that question? Now we answer that question by looking by geometrically. Let's answer it geometrically. It's easier. So we have one here and one there, and this is L1, that is L2. Now let me say that theta 1 and theta 2 can rotate by 360 degrees. Can rotate 360 degree full rotations. It has no joint limits. So what I'll get the shape of the work area as there'll be one circle here. Okay, this is one circle, and this is one circle, and then this is for rotation of theta 1. So theta 1 rotates by 360 degrees. I get the outer circle, which is L1 plus L2. Now then I rotate theta 2 by 180 degrees. What I'll be getting is another smaller circle like that, like this, right? That means the extreme point when this end effector can come, is still here. Okay, it can't go anywhere here. Now if I rotate theta 1, what I'll be getting is another circle like this. Okay, so how did I get it? First I got the outer circle, which is L1 plus L2. I rotated theta 1 by 160 degrees. Then I rotated theta 2 by 360 degrees. Okay, so first theta 1 rotated by 360 degrees, outer circle. This is equal to L1 plus L2. Then I rotate theta 2 by 360 degrees. So what I get is another small circle. So this is the extreme end where it can come. Then I rotate theta 1 again. This point I'm rotating by 360 degrees like this. I get this inner circle. So this is the area. This is the full area inside which the end effector can go. It cannot go anywhere inside there. Okay. So this is the shape of the work area. The end effector can go anywhere inside here, but it cannot go inside there. Okay, it's out of reach. So the question that we are trying to answer is what should be L1 by L2? We can say that the L1 and L2 should be such that the work area should be maximum. Area should be maximum. Okay. Now if the work area is maximum, then it can go anywhere inside the work area, and it's good. It'll be a good design, right? Now if you look at this figure, when would the work area be maximum? The work area, what is the work area? It is, if this is my V1, this is my V2, then the work area is V1 minus V2. That's the work area. And the work area would V1 depends on L1 plus L2. So whatever is that ratio A, it doesn't matter because the outer radius is always L1 plus L2. But the inner radius is L1 minus L2. Okay. So this is equal to pi L1 plus L2 squared minus pi L1 minus L2 squared, okay, in terms of area. And when will this be maximum? This will be maximum if I can make this one equal to 0. Okay, that means if V2 becomes equal to 0, then it becomes the full work volume. And when will V2 become equal to 0? So L1 plus L1 minus L2 equal to 0. It will become when L1 is equal to L2, which basically means that if the lengths are equal, then what will happen is this point will rotate like this and come till here. And there will be, this area will not be there, this will be a point. Okay, so basically what we are saying is if L1 is equal to L2, then what will happen is, this is L1, that is L2, and they're equal. Okay, then what will happen is you'll get one circle like this, and when this one rotates, it comes till here. So you're getting another circle, but it's a point. So the full area has become the work area. So what is the optimal link length? L1 by L2 should be equal to 1. Okay, so you'll always find that for different robots, the work lengths, the link lengths are always equal to 1. Okay, and whenever you look at a robot, you'll always find that the link lengths are equal to 1 because it will maximize the work area. So today we looked at joints, and we looked at the work volume, and we saw that different robots have different work volumes. So in the next class, we'll be looking at, we'll start off with transformations. What is position of a point? How do we specify, how do we put axis? What is an axis? And then we'll proceed with kinematics. So we'll stop here today. So thank you.